I will begin with a word of prayer. Dear Heavenly Father, we thank you for this time we have to meet and study your creation. We thank you for linear algebra. Help us to understand it a little bit better today, Lord. In your name I pray, Lord Jesus. Amen. All right, so I have, last time we finished proving the Cayley-Hamilton theorem, and, you know, there's all kinds of neat, like, silly questions that you can come up with from that. Because, I mean, if the polynomial satisfies the characteristic equation, like, let me just show you a silly example. This is just for fun, all right? But if, you know, the characteristic polynomial happened to be, let me use x instead of t for a second here. You know, x cubed minus 3x squared plus 10x minus 1, right? Then find the inverse transformation in terms of t, in terms of the transformation t. Is all of a sudden a problem that that you can do. In fact, it becomes an easy problem, right? Because what does the Cayley-Hamilton theorem say? So if this is the characteristic polynomial, Cayley-Hamilton says that if I plug in, you know, what? I have t cubed minus 3t squared plus 10t, right? Minus the identity transformation is equal to the zero transformation, right? So can I find the inverse? Well, yeah, I can. See, all I have to do is rewrite this as, you know, t cubed minus 3t squared plus 10t equals to the identity, right? And then what? Well, factor t out, right? This is t times, you know, t squared minus 3t plus 10 equals to the identity. So by our theory of inverses and the uniqueness of the inverse, what does it say? And of course that 10 is 10 times the identity to be fussy, right? But there you go. So the Cayley-Hamilton theorem, it has use that you might not expect, all right? It's actually a very powerful theorem. It does reveal much. All right, so, but we're moving on at the moment to look at the theory of the Jordan form. And so the context here is I'm going to try to keep it just about linear transformations, all right? So we're going to consider T, all right, T a mapping from V to V over a field F such that the polynomial of T and X, which I guess I could write as, you know, the determinant of T minus X, right? That's my characteristic polynomial, and I want to assume that that characteristic polynomial splits over the field. And by that I mean that it completely factors. So this can be written as, you know, let's say minus 1 to the n times x minus lambda 1 to the a1, x minus lambda 2 to the a2, dot 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 dot, x minus lambda k to the a sub k, where lambda 1, lambda 2, lambda k are in F and are distinct. All right. If I do that, then what does that make the exponents there? Well, those are what we call the algebraic multiplicities, right? So like here, the algebraic multiplicities. A1, A2, AN have what? Notice that they have A1 plus A2 plus plus A sub k equals to N, right? Now, it's not always the case, right, that the characteristic polynomial has to split over the field. Unless your field is, well, algebraically complete, right? Like if we're in the complex numbers, then this is always the context, right? Because any polynomial, nth order polynomial with complex coefficients can be factored into n linear factors, possibly repeated, of course, right? This is the fundamental theorem of algebra. But if we're working over the real field, we know that it's not generally possible to factor the polynomial, right? And so then we need some kind of special song and dance in that case. And so that's where my complexification construction comes into play, but we'll do that another day, all right? So this is somewhat limited. This doesn't hold for all possible linear transformations. It only holds for those for which the characteristic polynomial splits. But if it does, then it turns out that we can find the Jordan form. And so I want to try to describe that today. I'm not going to prove everything today by any stretch of the imagination. The proofs are all in chapter 7 of Insel, Spence, and Freeberg. And, but I think we've done enough that you'll hopefully not be too mystified by it. But we need some definitions. So first definition is k sub lambda. This is the this is the generalized eigenspace with eigenvalue lambda. And so this is a little bit slippery, but this is equal to x and v such that t minus lambda to the kth power acting on x is equal to 0 for some, k in, I guess the natural numbers probably would work. I don't know, do I need to have 0 included? No, I just say positive integer in my notes. So yeah. But this is the generalized eigenspace of lambda with respect to, this is all with respect to t, okay? It's all with respect to a given endomorphism on this finite dimensional vector space. All right. So I suppose you could write this as like, if you wanted to, this is actually what? This is like the intersection over, k in the natural numbers of what? The kernel of t minus lambda to the power k. Is that right? I guess it's not. Is it the intersection? I don't think I'm saying, it's not the intersection, is it? What is it? It's, anyway, this is the definition. We don't need to write that, but it's not the intersection. That's not right. They don't have to be in, doesn't have to hold for everyone. It's enough for it to hold for one of them, right? But here's the theorem that describes this generalized eigenspace. There's basically a few important features. So here's the theorem. This is my 4.52. Number A, k lambda is t invariant. It's a T invariant subspace. Just a point of reminder, E sub lambda was what? This was just the kernel of T minus lambda, right? That's the eigenspace for eigenvalue lambda, right? And so, so K lambda is a T invariant subspace of V. And, by the way, E sub lambda is a subspace of K lambda. Now that's not particularly a deep part of the theorem because you can pretty easily see that if you have an eigenvector, it satisfies the defining condition of K lambda with K equal to 1, right? So it certainly includes eigenvectors. Part B, for any eigenvalue, if mu not equal to lambda eigenvalues of T, then K sub lambda intersect K sub mu is equal to 0, right? Hey, that's just like we saw before for eigenspaces, right? We saw this for eigenspaces. The eigenspaces were independent like this as well, right? Their intersection was 0 for distinct eigenvalues. And then C, for any scalar mu not equal to lambda, the restriction, if we take T minus mu I and restrict it to K sub lambda, is 1-to-1 and, well, and onto. I don't know what that means. And onto. I mean context here. What am I meaning? I must be meaning, it's not really the restriction I'm talking about. I'm talking about, my meaning there must be T minus mu I viewed as a mapping from K lambda to K lambda. All right? So this is like this, I think, I don't have a notation for it, but it's like the T sub W, you know? So K sub lambda is an invariant subspace of T minus mu I, and with respect to that construction, it is a 1-to-1 and onto map. These are not easy things to prove, by the way. They involve like symbolic polynomial algebra, and they're actually pretty. So these are pretty tough to prove, these assertions, actually. Okay. Now, but once you have, so here's further theorem. This is 4.53. The dimension of K lambda is, oh, well, my notation is unfortunately not the same. The dimension of K lambda J in my current notation is less than or equal to what? Oh, this is, forget this. This is like a halfway house. Like, forget this, okay? Scratch this theorem. Let me just get to the main event, because we're not actually going to develop these ideas, right? So you don't really care about the intermediate forms of the theorem. This is like a step towards the actual result which we're interested in, which is 4.55. Sorry, guys. Burying the lead here. The point is simply that the dimension of K lambda j is just equal to what? So the answer is simply the algebraic multiplicity. So like a sub j. All right. Moreover, v is actually like k lambda 1 internal direct sum, k lambda 2 internal direct sum, k lambda sub k. That's the big result, is that we can see any linear transformation that, and I say this is theorem 455, but I'm interpreting it in its most interesting, like, this is not actually what theorem 4.55 says, so let me put some quotes on that, because I have taken theorem 4.55 and hopefully made it more interesting, all right? And so, like, in other words, this is the theorem we proved for eigenspaces, right? If we had enough eigenvectors to form an eigenbasis, then we can form the vector space as an internal direct sum of the eigenspaces, right? And then in that context, the matrix was diagonalizable with respect to that eigenbasis. So this is like the next level up. Maybe we can't find enough eigenvectors, but supposedly we can find enough generalized eigenvectors, all right, to form a basis that puts T into a particular form, and that particular form is called the Jordan form. So like part and parcel of this is you have like basis 1, basis 2, union union basis k, and corresponding to this, right? The beta 1 is a set of generalized eigenvectors for eigenvalue 1, and then generalized eigenvector for eigenvalue 2, and all the way out to generalized eigenvector for the kth eigenvalue, all right? And I'm claiming that we can actually put together what is called a Jordan basis for each one of these generalized eigenspaces. All right, so let me try to describe the structure there for you. So we need yet more definitions, all right? But before I get to that, in terms of the language on the board, can you describe for me, in terms of the generalized eigenspace k lambda and the eigenspace e lambda, what would it mean to say that our transformation is diagonalizable? What would we, how would that play out? Theorem. T is diagonalizable given the current context. Means what? Again, I'm assuming the context that we have a split characteristic polynomial, all right? All our eigenvalues are in the field. How about this? K lambda equals blank for each eigenvalue. What do I want there? So can you guys fill in the blank? What's that? No, no, no. It's got to be another subspace. K is a subspace, actually, right?
Something that indicates the algebraic multiplicity is 1 for all eigenvalues.
How about, well, we don't need that the algebraic multiplicity is 1 for all eigenvalues, but what we do need is the algebraic multiplicity is equal to the geometric multiplicity. See, because if we have that for every eigenvalue, then that means that your generalized eigenbasis is just plain old eigenbasis. So basically the beta 1 through beta k would just be eigenvectors, and you put them together. So in short, the mystery thing here was just E lambda. If your generalized eigenspace is simply eigenspace, right, then that means that your transformation is diagonalizable. That's the nicest case of what we're doing. But usually, in the wild world of linear transformations that are, not nice, you need generalized eigenvectors, which I'm about to describe, okay? So, what is a generalized eigenvector? Well, a generalized eigenvector of order p with eigenvalue lambda, all right, with respect to a linear transformation t, is a non-zero vector such that when you hit the p power of t minus lambda on it, it sends it to 0, all right? Yet, the p minus 1th is not 0, right? So, special case, p equals 1 is just what? So when you put p equals to 1, this just reduces to the 0th power. That's understood to be the identity transformation, right? So a generalized eigenvector of order 1 is just an eigenvector, plain and simple. All right? But the higher order ones are, well, less familiar. But we like to find them in what are called chains. So let me define that for you. A k-chain with eigenvalue lambda all right, of linear map T going from V to V, as we've been talking about, all right, is a set of K non-zero vectors V1, V2, Vk, such that, here we go, T minus lambda acting on Vj gives me Vj minus 1 for j equals to 2 through k, and T minus lambda acting on V1 is equal to 0. So, theorem, number 1, V sub j is generalized eigenvector of order j in the above. Number 2, V1, V2, Vk is linearly independent subset of k lambda. Now the fact that it's a subset of k lambda is pretty obvious, because these are generalized eigenvectors with eigenvalue lambda by their very, well, that's not clear yet. All right. But once we've proved part one, then the fact that it's a subset of k lambda is like obvious, because part one proves that every one of these is a generalized eigenvector and as such fits in k lambda, right? Now once we've shown that this is linearly independent, that shows us, hey, these are good things to build those bases beta 1 through beta k with, right? That k not having any relation to this k, by the way. Sorry. I've only got so many letters. I should probably make this like a p. It's not too late, I can make it a p. No? Okay, all right. So, first order business. This theorem I think would be healthy for us to actually prove, because this one I can actually test you on, and it doesn't require some sort of like dark heart of polynomial algebra that you've never learned, right? That really we teach that in 422. So yeah. All right, so generalized eigenvectors. So like, first of all, proof of one. So first of all, j equals to 1 by definition, right? We have t minus lambda, v1 is equal to 0, therefore v1 is generalized eigenvector order 1, right? Got that. How about j equals to 2? Now I gave you guys a homework problem that kind of hopefully got you started on this kind of algebra. But you might not realize that that homework problem is maybe more important than it looks at first glance. But j equals 2. So we've got t minus lambda times v2 is equal to v1, right? By definition of the k-chain. Take that equation, operate by t minus lambda. What do you get? Oh, hey, that's 0. So we have t minus lambda of a lesser power than 2 is non-zero, one lesser power, but t minus lambda squared on v2 is 0. Therefore, v2 is a generalized eigenvector of order 2. Right? I'll do 3 down here. J equals to 3. Okay? So we have t minus lambda on v3 is equal to v2. What do you think we should do with that? I think we should hit it with t minus lambda probably one time. Oh, you say 2?
Oh, I
Hold up a 3. I mean, we do want to get to 3, but there's a reason I should do it once, and you'll see that after I do it. So if I do it once, well then t minus lambda on v2 is what? It's v1, right? Which, by the way, is not equal to 0. And yet, when I take t minus lambda cubed on v3, I have t minus lambda on v1, which is 0. Therefore, v3 is generalized eigenvector order 3, all right? We can go on like this, yes? All right. So that's essentially the proof of 1. And you could clean that up with an induction, right? But there it is. How do we prove linear independence of v1 through vk? What are we going to start with there? This first example was just for fun. Did it look like fun? No? That was fun. That seems borderline, at least borderline fun. All right. Okay, so to prove linear independence of the K-chain, we do what? We say take a linear combination, right? Suppose you got C1 V1 CK VK is equal to 0. And may I humbly suggest that we look at T minus lambda to, I don't know, the K minus 1th power, acting on that. Right? But we just got done proving, right, that this is equal to, find the sum j equals 1 to, let's say, k minus 1 of cj t minus lambda to the power j acting on vj, yeah? And then we've got plus, my bad, not t, this was not j, this was what? K minus 1, right? And then, of course, I've got my ck, t k minus 1, t minus lambda to the k minus 1 acting on vk. All right. Now that's all. That's not good. Check these out. Think about that. The powers there, they're always either larger than the power, which makes the vector go to 0, right? Like, this is at least, like k minus 1 is greater than or equal to j in that sum, for every j in the sum. And therefore, by thing we already almost proved for part 1, these are all 0. Which then gives me this, right? Right here. But what was this? Well, that's not equal to 0, right? In fact, you can be more, if you really look at what happened, you can even tell me what that is, right? What was it? When we look at like 1 less power than the thing we're making 0, it always worked back to what? It always worked. See, if you look back, it always worked back to what? What's that?
The previous eigenvector.
Yeah, but it's not. No, it's not that. It's that's coincidental. But like, if I have, this is like the order 3 one, v3, right? When I get t minus 3, t minus lambda squared, we get v1, right? If I was to look at, for instance, t minus lambda to the 3rd power acting on v4, I would also get v1, all right? So like the thing we're doing over there, for arbitrary, I mean, it doesn't matter what k is, that actually works out to v1. So you get ck v1. Which of course then implies ck is equal to 0, right? But then you can just repeat this argument doing like lower powers. Then you can just do the same argument, but instead of doing like next, just do t minus lambda to the, k minus 2. And if that acts on star, would imply that ck minus 1 is equal to 0, right? And so forth. And continue in this fashion. obtain C1, which of course then shows us what? The K-chain is linearly independent. All right. There is a, all right, yeah. So the oh man. So theorem, there exists a basis for T formed by union of K-chains for T. And I'm being, to be more precise, I'm assuming that the linear transformation is got a characteristic polynomial which is split. All right. But this basis that I'm talking about, which is formed from a union of K-chains, is known as a Jordan basis. All right. Now you can prove that. Can I erase this? Here, yeah. All right, so let's look at the case that V is equal to just the span of a particular K-chain, V1 through Vk. All right. If we take this particular case, it's instructive. So here, where beta is K-chain with eigenvalue lambda. All right. For T, of course. All right, so then in this situation, what does the matrix of T with respect to beta look like? So we're looking at, okay, so we got T of V1, right? T of V2, T of Vk. All right. I think it's helpful for us to write, so what was the chain condition? The chain condition was, what was it? It was T minus lambda acting on Vj is equal to Vj minus 1, right? But let's take this is the so-called chain condition. And let's rewrite that a little bit. What that says is that T of Vj, right, is equal to lambda Vj plus V sub j minus 1, right? That is, I'm just taking that equation and rewriting it in a way which is profitable for the current question, namely, what's the matrix of the transformation with respect to a K-chain? All right? So now the first one is not like the others, right? The first one is just V1. The second one is lambda V2 plus V1. And this goes on. Lambda Vk plus Vk minus 1. Now you guys have had some experience with coordinates at this point. What are the coordinate vectors for these given that basis beta right up there, right? What's the coordinate vector of V1? This is just what? And am I right here? What am I missing? Something actually very important. What goes here? Lambda, yeah. All right. So what we've got is like lambda E1. This gives me lambda E2 plus E1. And it continues until finally we get lambda EK plus EK minus 1. Now we can write this as two separate matrices, all right? We've got lambda we can factor out, and we've got E1, E2, EK, right? But we've also got this other matrix which has got 0 in the first spot, and then E1, the next one would be E2, and this goes on until you get EK minus 1, right? So this, I don't know if you can see it or not, but this is the K by K identity matrix. All right. And like I can write this out as lambda times the K by K identity matrix. And that other thing I would call n sub k. So this is n sub k, which is, it's zeros and then ones right above the, one's on the super diagonal. Zeros everywhere else, all right? You can check that this matrix has n sub k to the k minus 1 equals to, it's got zeros everywhere except for the very upper right corner being 1. And so then n sub k to the k is equal to 0. So this is, this right here, guys, is the nilpotent order k matrix. I would say it's it's like the standard one. What happens as you power that matrix, it moves the super diagonal up, just pushes it up. So like, for instance, if I take 0, 1, 0, 0, 0, 1, 0, 0, 0, and I square that thing, I get this. So that's like n sub 3 squared. Whereas n sub 3 cubed is 0, all right? This thing I just wrote is the K by K Jordan block. So definition, J sub k of lambda is lambda times the K by K identity plus the nilpotent matrix of order K. This is the kth order Jordan block with eigenvalue lambda. Now, what I'm telling you, and I haven't certainly not proved, and nor will I, all right, the proof is in chapter 7 of the textbook, is that if your matrix has a characteristic polynomial which splits, if you have all the eigenvalues in the field, then if, beta 1 union beta 2 union union, let's say beta, let me say beta s, where beta, beta sub I is a, let us say, case of I chain with eigenvalue lambda sub I. And I wanted to call this whole thing beta. And, you know, beta is basis for V, then, and of course this is all with respect to, as usual, I keep forgetting, but, you know, given T, a linear mapping from V to V such that, you know, the characteristic polynomial of T is split over the field. So if we have a set of k-chains, all right, such that the union of them forms a basis for V, then the matrix of T with respect to the beta basis is simply J sub k1 of lambda 1 direct sum J sub k2 of lambda 2 direct sum. And here I'm talking about the direct sum of matrices. This is a way of making new matrices from old. And here I'm describing how we can build the matrix of T with respect to this Jordan basis as the direct sum decomposition of the Jordan blocks. This is the Jordan form of the matrix. And the theory says that this Jordan form is unique up to reordering of the blocks. Now, if I have, I'm not assuming here, I'm not assuming necessarily that the eigenvalues are distinct. Yeah?
Is that a phi or an S?
S, yeah. It is an S. Like a sneaky snake. Then that's the Jordan form. So, like, for example, what example am I on? I've lost track, but maybe did I even have an example today? Goodness. I feel like I had an example. Was there anything past example 1? Just one? Okay. So example 2, we could have like T is the linear transformation that's left multiplication by A with A equal to 3, 3, 3 with 1s above the diagonal. And then 7, 7, 1 like that. And then 3, 3, 7, 7 like that. If this was the form of the matrix, everything else 0. If that's the case, in this context, the standard basis is in fact a Jordan basis. And so like k sub lambda equals to 3 would be the span of something, and k sub lambda equals to 7 would be the span of something else. You guys tell me what those fill in the blanks here will be done for today. Well, almost done. I also want to know what the eigenspaces would be in this case. Remember, the eigenspaces are a subspace of the generalized eigenspace. So let me just, at the moment I'm working backwards from the pattern that we just derived over here and these. So like this right here tells me that E1, E2, E3 is 3-chain with lambda equals to 3. This right here tells me that E4 and E5 is 2-chain with eigenvalue 7. All right? These are just eigenvector, these are isolated 1-by-1 blocks, so these are just 1 chains, which a 1 chain is just an eigenvector on its lonesome. So to build the generalized eigenvector, generalized eigenspace of eigenvalue 3, I would just do like E1, E2, E3, and throw in, let's see here, 1, 2, 3, 4, 5, E6, E7. And the generalized eigenvector, here I want E4, E5, 1, 2, 3, 4, 5, 6, 7, E8, and E9. That would go into this. And my eigenspaces here are just E1, E6, E7 for the 3 eigenspace. And for the 7, I need E4, E8, and E9. So let me just point out what I'm saying here is that every Jordan block in the matrix corresponds to the existence of one eigenvector in your generalized eigenbasis, your Jordan basis. Every block gets one eigenvector. And if it's more than a 1-by-1 block, then you also have generalized eigenvectors. So this block comes with one generalized eigenvector of order 2 and just one generalized eigenvector of order 3. All right? Anyway, I'll try to look at more examples next time with you guys so we can try to better understand like the pattern here. But, oopsie. Well, anyway.